catch or Sheetal's talk, because now we really want to get into machine learning and the introduction to machine learning and neural nets. So Sheetal, I want you to be able to unmute yourself and present yourself.
Hello, everyone. Hi, I hope everyone can hear me and see me as well. So thank you, Peter, for inviting me to the talk. I'm really glad that I could discuss the introduction of machine learning and deep learning with you and with everyone. So my name is Sheetal Reddy. I work as a data scientist at AI Sweden. Prior to AI Sweden, I was working in a couple of companies like Xilinx, Siemens as a research engineer, where I predominantly worked with intelligent video analytics platforms. And my background is bachelor's in computer science with master's in computer vision, machine learning, and deep learning. Yeah.
Great, and thank you, Sheetal. And you were, when you started working for AI Sweden, this is very interesting regarding the hackathon and how we met you, because you really out-brilliant everyone else at a hackathon, and that's why that's how we found you, and that's why we kind of figure out that we need to work with you. So just give them an introduction to the Bird Hackathon.
Yes, sure. So yeah, a very interesting story how I got to know about AI Sweden is I participated in a hackathon called Baltic Seabird Hackathon. So the whole idea about the hackathon is there are these seabirds which come to the island of Storakal. So once in a year, they stay there for 3 months, and the researchers of SLU wanted to use AI to understand the behavior of these birds. So they have installed a video camera on one of the ledge of these islands, and they were manually looking at the videos and noting down, okay, when did the bird come, when did the bird leave, things like that. But then they came to us for, as in they came to AI Sweden for help, and AI Sweden organized a hackathon, and we solved the problem for them. And fortunately, our solution was one of the best, and I also got a job at AI Sweden that way.
Yeah, but now you're here to introduce everyone to machine learning.
Right. Yes.
I'll give the floor to you, and I will stop sharing my screen.
Yes, so I'll start sharing. You should, I think you need to enable me to share.
Now we can do it.
Right, thanks. Right, so I hope everyone can see my screen now. Yeah, glad to be part of the session and talk about introduction to machine learning and deep learning with all of you. So yeah, let's dive into the details. So this is the third session as part of the AI crash course organized by AI Sweden and Women in AI. And the whole goal of this session is to acquaint you with the basic terminology of machine learning, some basic algorithms, and also neural networks. So a little motivation before I dive into the topic. This is a very famous picture. I hope everyone has seen this picture before. It's a picture of Margaret Hamilton, who headed the software team of Apollo mission. So, and right beside her is a stack of code. It's supposed to be code that she has written for the mission. This is particularly inspiring to us because she has been part of the pre-women liberation era in a field which is still tough for women to crack into even now. But the most interesting fact about this is if I have to mimic a picture of a data scientist from this, it looks something like this. So back in those days, people used to write a lot of code in Fortran. But now, with the help of different deep learning frameworks like TensorFlow and PyTorch, the current data scientist, doesn't really have to write too much of code, which gives an edge to get started with machine learning and deep learning very quickly. So this is one motivation to do this course, I guess. So let's dive into the details now. So what is machine learning? You have been listening to the term artificial intelligence, talking about it for the past two sessions. So by now you would have understood that artificial intelligence is a study of pattern recognition or enabling machines to think like humans or mimic human behavior. And machine learning is just a way to achieve artificial intelligence. There are different techniques like rule-based systems, but in machine learning, what we do is we learn the insights from data. So, and then the deep learning is another subset of machine learning, which uses deep neural networks to get these insights from data. So that's a basic difference. A lot of beginners get confused with what is machine learning, what is deep learning. So I thought I'd clarify this right in the beginning. So currently there are three ways to approach a machine learning problem. One is supervised learning, the second is unsupervised learning, and the third is reinforcement learning. So to simply put, supervised learning is like classroom learning, where a teacher will tell you what is a right answer, what is a wrong answer, and then you learn from what the teacher has taught you, and then there's a test at the end, whether how well are you doing. So that is how this works. We'll talk more about supervised learning in our later slides. So then what is unsupervised learning? Unsupervised learning is where you don't really you don't really have the target variables. That is a learning that you do outside the classroom, where you try to find patterns in the world. So in the same way, the AI tries to find patterns and cluster them together in the data set. And then there is a third kind of learning, which is called the reinforcement learning. So reinforcement learning follows a little different different style. That is, it is used to train AI on tasks that are not fully comprehensible or understood by humans. For example, walking. If you are supposed to teach someone how to walk, how do you tell them? So I raise my leg, I put it down with an angular velocity. No, you don't do that, right? No one understands, and it neither makes sense to you or to the other person. So then how do you train an AI on skills like walking, going from one place to another? So the reinforcement learning is used in tasks like that, where the AI is given some rewards or punishments when it has done well or when it has not done well. So this is exactly how a small kid learns to walk. When he or she tries to walk, they get up. And then they fall down. Fall down is kind of a punishment. They get up and move forward. It's kind of a reward. So that is how you learn these skills. And this is exactly the way you teach an AI to do that as well. So yeah. So in this session, we'll talk more about supervised learning, which is a very straightforward kind of learning. It is where the teacher or someone, a human, gives AI answers to learn first. So in supervised learning, the data always exists in pairs, that is a sample and a label. If you have an image of an apple, you have a label that it is an apple, and then you create these pairs, and then you let the model learn from these pairs the distinguishable features in the image. And then when a new image of an apple is given, then the model will understand that it's an apple because it has learned from its previous knowledge. It has learned the insights, and then it'll give you an output saying that it's an apple. So it's a most straightforward way of learning. And we will we will do a group activity on supervised learning. We will work with a data set called MNIST dataset, which is a handwritten digits dataset. So you have digits from 0 to 9. All the handwritten images are grouped together and then created a dataset. And then you are supposed to classify these images into all the 10 classes. So we'll work more on this in the group activity. So before that, let's dive into, or let's know about the basic machine learning terminology. You might have heard about these different terms. So the process starts by us getting hold of a data set. So we get a data set, and then the first thing we need to do to train a model is split the data set into training data and the testing data. So the training data is used during the training phase, where you use the data to learn a model, and then you use the testing data to validate this model, whether it is performing well, it is making some mistakes, something like that. So you can also call testing as inference. So inference time is specifically important. You see this a lot many times before. What is the inference time of the model? People ask. So it is important because a model can't just take 5 minutes or 10 minutes to run on a single image. So inference time is the time the model is taking to run on a single data sample. And we have talked about this before. If data exists in pairs, one is a sample, the other is a label. The label is also called as ground truth. Data scientists like to call it as ground truth. So yeah, you can keep that in mind. So, and model. So we keep talking about models, training models, but what is a model? What exists inside a model? So let's look at this in the next slide. So a little bit of mathematical intuition. This equation y equal to wx plus b. You're going to see this equation again and again in this presentation, not just in the presentation. If you are going to know more about machine learning, deep learning, then you will see this equation more than often. So y equal to wx plus b. What is y equal to wx plus b? Y is the label of an input example and X is the input example. So we have discussed that data is always in pairs. So Y and X, we already have Y and X. But what are W and B? So W is the weight and B is the bias. And we don't know what W and B are. We don't have them. What we have in our hand is a data set, which is Y and X. Now, how do we figure out W and B? Is the whole machine learning and deep learning. How do we figure out W and B, the weights and biases? So when you look at this equation, y equal to wx plus b, does it ring any bells? Very similar to something we have learned in the math class in school. It's an equation of a line. It's an equation, it's very similar to y equal to mx plus c, where m is the slope and c is the intercept, where the line intersects the y-axis. So yeah, I am pretty sure everyone remembers this. So y equal to wx plus b is essentially a line, and this line is our model. So our model is the and our model is this line. But why is this line very important to us? So you might not just see y equal to wx plus b, but you might see many variations of this equation like this, a weighted sum of features. So you might see many variations of this, but what is this model? Why is it important? So that will so we'll see it here. So For example, let's say I have a data set of dogs and cats, and I somehow plotted them on the axis here. So, and then this is my training data, and now I have a test sample. Now the task is to classify this test sample either as a dog or a cat. And how do we do that? So let's draw a line. So let's draw a line and say that, okay, the samples that exist on the left side of the line are cats, right side are cats, and the left side are dogs. So according to this line, the green sample that we see, the test sample, is classified as a cat. Now, is there only one line that passes through this data set that distinguishes both of them? No, there can be many lines. So different lines have different slopes and intercepts. That means different lines have different weights and biases. So this is a linear line, but what if the data set is something like this, where can we draw a line through this data set to distinguish between rats and squirrels? They look a little similar, right? At least in this data set, no. Your decision boundary is not a linear line, but it's a curvy polynomial. So it is this means it is the data set is not linearly separable. It means the data set is non-linearly separable. So your decision boundaries, whether it may be a line or a non-linear equation, this is the model that you are supposed to find out which will be suitable for the task. For example, here it's classification. And how do we find out these values, the weights and biases? So supervised learning, till now we have looked at classification. So supervised learning, there is something else under the umbrella as well, which is called regression. So what is the difference between classification and regression now? So previously we have looked at cats and dogs. So cats, dogs can be encoded into real numbers. Like cat can be 0, dog can be 1. So you can classify them into different classes. But in regression, if you use regression, your output can be a real number, that is 3.14, 2.56. So now you understand for which task you can use what. If your output you think is supposed to be a float number, then you use regression. But if you want your output to be a integer, then you use classification. So a little bit of information about regression. So why do we use regression? So here, if you see, there are a lot of points, and then we try to fit a line in regression. This is basically linear regression here, because the line, it's a linear line. So what we do here is regression makes us understand the relationship between a dependent variable and an independent variable. So y equal to wx plus b. X is an independent variable. Y is a dependent variable which depends on X. So in the same way, this regression model will give us a relationship between the independent and dependent variables. And at times when we know the independent variable, we can predict the value of a dependent variable using linear regression. And how do we do that? In linear regression, we try to fit a line that passes through most of the points. And the way we do it is we take the y offset, that is the error between the points and the lines, and we take the line that gives us the least error. So that is the best model for your data set. So this is called least squares error, and that kind of model can best describe your data set and can be used to predict your future points. So yes, so when we take this equation y equal to wx plus b, I've told you guys, this comes again and again. So when we take this equation y equal to wx plus b, what is x? X is x can be anything, but what if x is an image? Will you give a image vector? Let's say the image is around 100 cross 100 pixels. You can't just give the 100 cross 100 pixels here and optimize, right? So we do some kind of feature engineering. So let's say our task is to distinguish between cats and dogs. We have to figure out what is x1 and x2. So a data scientist have to pick what are the most distinguishable features from the cat and the dog and use them as a input feature vector. So here, let's say I picked up two features, that is ear size and tail size. It can be anything. But it takes some effort from the data scientist side to understand what features are distinguishable, and then you try these features, and then you train a model, and then you validate the model. But if the model doesn't perform well, then you go back, take different set of features and do the whole process again. So there's a bit of effort that goes into feature engineering if you use traditional machine learning algorithms. So that is where the difference comes in machine learning versus deep learning. In machine learning, someone has to sit down and then do feature extraction, as in has to figure out which features are best and then give it to the classification algorithm, and then that gives an output. But the best part about deep learning is you give, for example, if you're dealing with images, you give an image as is to the network, and the network will figure out the best features that are distinguishable from dogs and cats. So that way, that is why deep learning has become so much more popular, because it is so much more powerful than the traditional machine learning algorithms. But there are a lot of work, there's a lot of work also going in deep learning, which is called as representation learning, where you where we model the architecture of the neural network in such a way that it learns distinguishable representations. So yeah, a lot of research is also going on in the side, but it's this is a much better phase than a few years back, where people used to handpick features and then give it to a classification algorithm. So let's talk about a very basic classification algorithm called k nearest neighbors. So let's say k is 1, then it is 1 nearest neighbor. So how does this work is, we have some training data plotted here, and let's say we have a test data set, this sample coming in, and then we have to figure out which class this data sample belongs to. And what k nearest neighbors does is, you figure out the machine learning algorithm figures out the most nearest neighbor. Let's say, for example, this is the most nearest neighbor to this test point. So the test point will be green. So let's give the class of the nearest neighbor to the test sample. This is a very simple classification algorithm. For example, if the point is somewhere here, the test sample, then if there are 5, if the k in the k nearest neighbors, let's say if k equal to 5, it seems like there are 3 here, 3 nearest here, or 2 nearest here. The majority belongs to this class, so it is yellow. So it's that simple. So it's the simplest classification algorithm available. But the problem is, how do you choose k? You don't really have any rule to choose k. You have to, it's completely trial and error. So the lower values, if you have lower values, that is, if k is just 1, then it is easily affected by outliers. And if k is too huge, then of course it smoothens out. But it's better to choose a value after a lot of trying out. So but what is the model in k nearest neighbors? So we are not drawing any lines. We do not have any model, as in we do not draw any curves here. So what do we call as a model in KNN? So the model is the whole training data. So whenever you get a test sample, you need the whole training data to understand to understand which class the test sample belongs to. So the model in KNN will be the whole training data. So coming to the most fascinating algorithms, neural networks. Neural networks are really very fascinating because they are inspired. The architecture is inspired by how the human brain processes information. The basic unit of a neural network is a neuron. So this kind of architecture is called as a multi-layer perceptron model. We are currently not using multi-layer perceptron models, but this is the first architectures that were used. So the multi-layer perceptron model. So the basic unit is a perceptron. A perceptron is essentially a neuron with inputs and activation and the required outputs. So how do we train neural networks? Depending on this, so let's get a little mathematical intuition of how to train these neural networks. So the same equation comes up, which is y equal to wx plus b. So the output of a perceptron is always a summation of weighted input, and we give it to an activation function called f. We use an activation function because remember we had this non-linearly separable data sets and linearly separable data sets. So to get the non-linearity into the models so that they can classify the non-linearly separable data sets as well, we need to bring in something called as an activation. So this activation brings in the non-linearity into the perceptrons. Otherwise, it's always going to be y equal to wx plus b, which is always a line. So this brings in the non-linearity into the models. So what is a neural network essentially doing? We are giving the input and then we are getting an output. We are mapping the output to a certain input. That means we are figuring out a function which maps an input to an output. And our whole goal is figuring out what is this function. And how do we do that? We train the model. So how do we train a model? So initially, you can also imagine a child, and you can imagine a child who is just born as a neural network, it's a biological neural network, but very similar to the artificial neural network because both are inspired from the same architecture. So they are initialized initially with random weights. Imagine a kid who has come into the world. He or she doesn't understand anything. It's random in their brain. So in the same way, the neural network is initialized with random weights in the start, and then there's something called forward pass. Forward pass is where you send in an image, and then because the weights are random, you get a very random output. And what do we do now? We sent a cat image and we are expecting a cat image, but we got some random output. So what we are supposed to do is figure out a loss function or the error. Let's say you want a value, you want a value 1, but you are getting something like 0.5. So you figure out the error. What is the error? So the error, let's say the simplest error here would be the desired value minus the predicted value. And that error is back propagated and the weights are adjusted to improved weights. So that is the process of training a neural network. So this back propagation algorithm, when you back propagate the error into the weights for adjusting, you use something called gradient descent. I'm not going into the mathematical details of gradient descent, but you could as well look up on Google and you'll get a number of blogs on this. So yeah, so and then uh, you back propagate and adjust the weights, and you do this multiple number of times. For example, you do this for multiple iterations, 6, 7, 10, 100 iterations, and then the weights are adjusted to what you decide for in the end. And then when you send a cat image, then you'll get an output cat, and when you send a dog image, you'll get an output dog. So this is how the neural networks are trained. But there is a lot of mathematics behind it. It's good if you can go back and look it up on Google. There are a lot of blogs which have really made it easy for beginners to understand the gradient descent and back propagation algorithm. So now we know how multi-layer perceptron models work. Now let's talk about convolution neural networks. So in convolution neural networks, so what is so different? Here, what we do in multi-layer perceptron is, if you have an image, let's say 100 cross 100, you convert the two-dimensional vector into just a single dimension vector and then give it to the image. That means give it to the network. That means you're distorting the image completely. So what you do in CNNs is you preserve the spatial and the temporal context of the images as is. So you do not create, you give the image as is to a convolution neural network so that it learns the context in the images. So in convolution neural networks, it's there are something called convolved features. These features or filters are the weights that you'll be learning that are the weights and biases that you'll be learning, and they are part of the model. So the most important and basic unit of a convolutional neural network is this convolution. So and in the same way as multi-layer perceptrons, these also have an input layer, output layer, and a lot of hidden layers. And these hidden layers have multiple convolutional layers, pooling layers, normalization layers, a lot of different layers which do different mathematical operations. So because of all these operations put together, it was actually possible for image classification to have such higher accuracies. So it's really important to understand convolutional neural networks because no one is using multi-layer perceptrons nowadays. It's just CNNs. People are using predominantly CNNs in every area. So it's the basic block is just a convolution operation, and then you add on more and more layers to it. And because you are adding so many layers to it, this is called deep learning. So you're increasing the depth. And then there is another interesting neural network architecture, which is called generative adversarial networks. So till now, we have been talking a lot about networks which are used for classification. So these are essentially called discriminative networks because they learn this distinguishable and discriminative features between classes to distinguish different classes very easily. But this generative adversarial networks are a little different. They are equipped with so essentially you give them a noise vector and they can generate a full realistic image from them. So these are called generative models, and till now we were talking about models which are discriminative. So how does a GAN do that? So a GAN is basically a generator discriminator architecture. So a generator tries to generate artificial samples from noise vectors, and a discriminator takes these samples and then classifies them as real or fake. So imagine you put this generator and discriminator in a competition. So the generator has to fool the discriminator by producing as realistic images as it can, and the discriminator has to perform so well that it can still classify the generators images as fake. So they are put in a game theory kind of way, so in a competition, and that makes them improve their models. So will achieve a place, a conversation at convergence. The generator will generate such realistic images that the discriminator cannot really understand whether it's fake or real. And that's when you get face images like this, which are super realistic. So there have been a lot of improvements in GANs from the time they were introduced by Ian Goodfellow in 2014. There are a lot of variants of GANs where you have a lot of power over them, like conditional GANs, etc. Of course, you can look it up, and there are a lot of blogs on them as well. Yes, so we have a group activity planned using teachable machines, and the dataset is the MNIST dataset I was talking about, which is available on the Drive link. So maybe we could do that in the group labbing activity later. But I would like to just end my talk with this slide. I hope you understood what I was trying to say. And if you have any doubts, any questions, or if you want to do some interesting projects with us, feel free to email me. I have my email ID here. Yeah, and that's it.
Sheetal, thank you so much. I think we will do like this. We will go into the next part of the activity, and what we might do is that we will do the labbing and the teachable machine as a homework until next time, so that people have more time.
Yeah, sure.
We will introduce this in the end of the talk. Are there any questions? We have to start with that Q&A session with Sheetal. Otherwise, Sheetal, thank you so much. I think you will stay during the last bit here as well. This is great, and we will definitely post this as well afterwards, because this is a presentation I think a lot of more people can take part of. But what we will do now is to go into the next session, and as you know, we talked about this. This is one of the reasons we talk about problem solving and why we need to solve problems, the sustainable goals, or the sustainable development goals. And this is our our segue into the next segment and into Sophie that will introduce Gustav, because Gustav is involved in service design. He did his PhD in service design and also a tech entrepreneur. And I think I want to know more about how you solve problems and how you think about problem, Gustav. But I will let Sophie introduce you.
Awesome. So I'm back. So just to introduce myself quickly again. So I'm Sophie, and I'm representing Women in AI today. And I'm super excited to have Gustav with us here today. So Gustav is a tech entrepreneur. You are currently carrying out your PhD in cybernetics design and captology, which are concepts that are completely new to me, but that I'm very, very intrigued about to learn more about. So Gustav, welcome up and welcome here.
Thank you very much, Sophie. And
Awesome.
it's a...
How are you?
Yeah, I'm doing fine, thank you. It's getting dark so early these days, so that you know, keeping the energy up to the end of the day.
Awesome. Yes, we're very much trying to keep the energy up here, all working from home now. So as you might be aware, we've been seeing each other physically about 20 people each time, but then we've had a big digital room of around 60 to 70 participants each time. So that's super exciting. But Gustav, I'm just going to start. I mean, you're a curious mind, and you've explored areas from intelligence analysis in the Swedish Air Force. You've taught at NASA, Silicon Valley, and you've founded several companies, among which one is actually an education company or a student matching program called SCORE. And all of this, I assume, have led to the research that you're doing now in captology. And what I read up on this weekend as I was looking into captology, I learned that captology is the study of computers as persuasive technologies. And then design cybernetics. But can we maybe just start, or could you start by just what captology is? And I know that you're going to present a few slides on this, but just to have everyone on the same page, what on earth is captology?
Absolutely, thank you, Sophie. Yeah, well, I can actually jump straight into the slides. Actually, it might be a bit rude, but
no, it's perfect.
But I think it will explain itself better if I jump in there. Hi everyone, it's so lovely to be here, and I am so glad that so many of you have shown up this evening. So let's see here. Here we go. Okay. Are we all on the same page? We are on the same page.
Yes, we are.
Okay, yeah. So I'm going to talk a bit about the relationship between persuasive technologies, design, and AI. And as Sophie mentioned, I am currently a PhD candidate at the Royal College of Arts in London, focusing on persuasive tech and design. So I spent roughly 10 years working with startups, different startups, but predominantly an online digital marketing agency that I co-founded quite some time ago. But what I realized when I was working with digital marketing was that, I can sit here in Sweden and influence what people do on the other side of the planet. And I just found that fascinating. And then I stumbled upon this topic called captology, computers as persuasive technologies. And I spent the past 3.5 years trying to get a deeper understanding of it.
Sorry, Gustav, how did you stumble upon that? Because I'm not sure how many of us are familiar with the concept of captology from before, but how do you stumble upon such a subject?
Yeah, that's a good question. So I was actually introduced to it by the professor who later on became my tutor at the RCA. So he was studying, I spent an awful lot of time, surfing the web, just trying to find, different interesting things. And around that time, I had my radar on for PhD programs, and I was sort of looking at different research areas. And I first stumbled upon the captology lab at Stanford, which was founded roughly 20 years ago. And I read about all the amazing things that they did. And then I bumped into this professor, Ronald Jones at the RCA, who was working on the next step in persuasive technologies, which was sentient computers, or the idea, the theoretical and speculative idea that computers could one day have a conscience of their own and be sentient on their own merits.
But this is like a captology next level then. It's taking it further.
Well, this is the speculative future, you could say. And that's the speculative future of artificial intelligence as well. The idea that computers one day will develop their own kind of intelligence and their own sort of consciousness. But we're still, we're pretty far from that at the moment. But if we, future has a way to surprise us, right? We didn't know 20 years ago that we would sit here today, spread out around the world, and be able to have these conversations either. So there's a lot of cool things that can happen in a fairly short time. yeah, so, but I think what sort of drew me in, what I've kind of, because I came from the tech side, you know, I was working with tech companies, had a business background, and I've been hearing this sort of startup talk for 10 years. But then when I ended up in the arts and design school, it was like a different language was added to the tech language. And I think what I'm going to just go a little bit into is the relationship between design and technology, in a sense, in the context of persuasion. So the first thing that I want to share, that is kind of a backdrop to how this will influence us and influence society going forward, is that everything around us is designed. If you look around you, the rooms that you're currently in, the environments that you move in every day, they're artificial environments. Almost every single object in these environments are man-made. So we've shifted from sort of this physical jungle to an artificial jungle that is designed by people. We live in the consequences of other people's design decisions. And this effectively makes up a choice architecture around us of what we can do and what we cannot do. And sometimes the environment sort of physically restrains us. There is a wall in the way, or there is a window we can open, or, you know, stuff that we can pick up. But what's around us puts limits on what we can do and what we can't do. And in order to navigate these jungles, back in the days, we developed heuristics, mental shortcuts that guides our behavior. So that when we encounter something of a certain color, say that we go out in the forest, we see some red berries, it signals to us, you know, don't eat these berries. And we kind of have these heuristics built in as a survival mechanism. It's estimated that up to 95% of our daily decisions aren't reflected on, but that we act automatically when we see something and we act on it. But that also goes for the designed objects. So if you go into a grocery store and you see this red color, you know, you automatically connect it to that soda drink. So as designers, we work effectively with heuristics to instruct people how to use different objects and how to handle them. And to the idea of artificial intelligence in a design context is that since we came out of the jungle, we've always used different tools to act our agency in the world. So the shovel, for example, or just this, Sheetal, was developed as a way to help us to move and act in the physical world, to be more effective in shoveling earth around. But we're now developing cognitive tools as well, where computers are the most predominant tool that comes in many forms and shapes that helps us to extend our cognitive agency in the world. Right, so that we moved from kind of changing and designing physical tools to designing these cognitive tools that helps us to be stronger, to helps us to calculate better, to spell better, to communicate over larger distances. But this also means that since we live in this designed environment, and a larger share of the environment is larger share of the environment is also becoming computerized, so that we spend more and more time in using digital media. Designers are sort of not only making choices easier for people, but we're also actively designing choices for people. And this means that every time you design something to have a certain function for someone else, where you have an intent as a designer, you actively contribute to influencing the behavior of other people. And this kind of sounds scary, but we do it all the time. You know, persuasion is part of our daily repertoire, whether it's persuading a 5-year-old to get their clothes on and go to daycare center, or to persuade your boss that you should have a raise, for example, or negotiating with clients, small things, big things. We are influencing each other all the time. But what's happening with these more powerful technologies is that we're sort of moving more towards the act of sort of steering and controlling people's behavior using digital technologies, but also the physical environment. The physical environment is static. Well, most of it. I mean, it's if you have put something on the ground, it's you expect it to be there when when you leave the room and get back. Some of you might have heard about nudging. Nudging is the sort of the art of shaping things in the physical environment, so that it implements a certain policy. So it's behavior change using design of the physical environment. And in this example, they put out some footprints on the ground to lead the people up to the trash bin, guiding people towards a certain behavior, that is, toss things in the bin. But the same logic also works online, of course, where adding a bit of color to a certain part of the choice architecture online steers us towards that particular choice. So that was a very long intro, Sophie, to bring it to your question, your original question, which is what is persuasive technologies? So persuasive technologies are technologies that are designed with a specific intent to influence people's behaviors or attitudes. So on the left, you can see a speed bump. That is a nudging intervention. You can call it a design for behavior change. But the speed meter on the right, that's an example of a persuasive technology, is where you use the properties of the computer to interactively and actively persuade people to do something that you want them to do. And since we spend more and more time in digital rooms, I spend an average of, I think, 3 hours per day on my smartphone. And that's by no means an exception. I think most of us spend an awful lot of time living life through a mediated layer or through different services. This means that we're handing over a large share of our agency and our cognitive decision-making to these services. And some services have more power than others to guide and steer behavior at scale, because they set the standard for millions of other apps in these ecosystems. The main difference between this online choice architecture and the choice architecture of the real world is that it's interactive. It's changing. It's like if the walls would change color every time you visit a room, if you would be met with sort of new objects around you when you enter a garden or something. As an example, and this is just one example, there are lots of examples of how this interactive choice architecture works. Is, you get custom recommendations when you're using Netflix, when you're using eBay and Amazon, which is powered by artificial intelligence and machine learning algorithms. So that's how how design connects and interfaces with the amazing sort of technology that you were presented in the former presentation, the algorithms that are working behind the scenes, how they work to sort of influence us. This is kind of important to understand, because most companies invest an awful lot of money in trying to understand how we behave, and also to calculate and predict how we will behave in future. And invest a lot of money in different kinds of analytics softwares to essentially influence our behavior in different directions. And all this is powered by computers, and computers are constantly changing shape. And this also means that the persuasive abilities of the computer, like the opportunity space for different ways to persuade, increases all the time as computers change, opening up for new types of persuasive technologies. And computers think rather differently from people. They can be more persistent than humans. They can offer greater anonymity. They can manage massive amounts of data. They can persuade using different modalities. They can scale easily, and they can go where humans aren't able to go. And all these properties together enhances our agency in the world, our cognitive agency, times the power of computers. So through the lens of design, this shapes consumer behaviors, this enables new services and products, but it also raises an awful lot of questions about what is ethical and what is desirable. And I'm going to hand it back in just a second. I'm just going to show you 2 examples of what we're working on right now in persuasive tech research. And I'm more than happy to, just email me if you want to get more details about anything, because this is really sort of the crash intro. So we're looking into new forms of persuasion. What happens when computers can do this and can do that? What happens when, for example, realism of images of people come to a certain level, so you can no longer distinguish them from human beings? We look at personalized persuasion, we look at storytelling, subliminal persuasion, persuasive games, and stuff like that. We also look at interfaces, actually. We are really curious about what happens when you get human-like realism in different media, when you can design influencers or avatars that are indistinguishable from the real thing. They don't need to really pass the Turing test about being intelligent or being intelligent technologies in a way that you can't sort of. But if you can't visually sort of distinguish them from the real thing, it opens up for a lot of different problems. Like you can be deceived more easy or coerced into thinking that these things are human. And it also, as for designers, it opens up for all kind of tricky ethical areas. It's very common with new chatbots, for example, that they are abused heavily for the first time that they're out. And during that time, the designers need to learn how to deal with abuse of, say, virtual humans, chatbots, AIs, etc. Because you need to hard code them into how to handle different moral situations or ethical situations. Like in this case, the chatbot, the financial chatbot, had been asked out on a date nearly 2,000 times. It's been asked to send nude pictures more than 1,000 times. And the question is, how do you respond to that? These designers, they sent a picture of a circuit board every time they got that question. But there are many sort of layers on ethical challenges here. Should you create chatbots that are proactively educating users in how to deal with them, etc. Yeah, so that was a very sort of brief intro to design persuasive tech AI. And I'm sure that you have more questions than answers at this stage.
Wow, definitely. Yeah, thank you so much, Gustav. This is very, very intriguing to get an introduction to. But yes, I think I personally have probably more questions than answers. So I'm gonna shoot, and I'm gonna start with my initial questions, both that I had thought about from before, but also that arose during the presentation. And then we're also receiving a lot of questions in the chat. So guys, please go ahead and continue to ask questions in the chat. But one of the first things that I'm wondering about, or that I sort of want to clarify, because you mentioned that you got interested in capitology and sort of founded at the Stanford institution. What I wanted to clarify or ask, like, how old is this field? Because I understood that it's quite young and new. And how did it come about?
Yeah, well, so the idea of sort of computers or automatic machines being able to persuade humans has been around for quite long, but computers as persuaders has really it was really formulated by B.J. Fogg at Stanford's capitology lab. He wrote his PhD dissertation about charismatic computers. But prior to that, there's been an awful lot of discussions about computers as computers as humans, going back to the Turing test, for example. The idea that a computer could deceive a human into tricking humans that it's not a computer, that is real. And of course, there are a lot of works of science fiction as well that has played out these scenarios. But I think it was with the proliferation of the internet and also with social media around that time, around the 2000s, where, well, the home computers started getting out into households, that it also became a very real and tangible issue. And Foggy sort of captured this, and quite a few of the services that we see today are based on theories that came out of the Captology lab. So Instagram's founders, for example, one of them was a student of BJ Fogg, formulating this idea that, you know, you post a piece of content, someone clicks on it, you then get a bit of dopamine, and then you click on it again, and you keep posting and posting, and eventually you're doom scrolling. That addictive loop was one of the early findings from the lab that later on was turned into, became the gold standard for online persuasion.
Yeah, it's extremely interesting that there are so many sort of interrelating fields. Like here we're speaking about design, we're speaking about AI, but it's also obviously a lot to do with psychology as well. And then like when you're speaking about design, and we haven't spoken anything about design cybernetics, or I don't know, have we?
Yeah, cybernetics is an interesting, but it's a longer story.
Okay, so let's save it for another time.
Yeah,
But in terms of design, before you came here, I had the idea that you were relating basically the outer surface of this artificial intelligence layer or model, like basically the back end of the algorithms or the machine that we were looking into, and you were looking at, okay, what are they spitting out and how can I communicate this to a user? So I really only thought about it in a digital environment, but you've also shown a lot of situations from a physical environment. Like how do you view design, or how do you define design?
Yeah, that's a great question. I mean, I think in a sense everything that relates to artificial intelligence is design. I mean, the programming languages are designed by someone. The code is designed by someone. I mean, you can have a broad or a narrow take on it. I think from the perspective of human-computer interaction, that's a lot of design, or what we refer to as design today. So design has gone from 100 years ago, design was arts and crafts. It was architecture. It was the physical objects, industrial design. But these days, design has moved from that to service design, to experience design, and to transformation design, behavior design, that we're working with completely different materials today than traditionally. When you think of design, you know, you think of Svensk 10 and chairs and
yeah, exactly.
clothes, but you don't think of the atmosphere in a room. When you go into a cafe, for example, all cafes serve roughly the same coffee, but it's something that makes you choose one cafe over the other. So that is service design. And a lot of what we see here with AI is about interfaces, is how we humans interface with these computers, with algorithms. It's the service layer, so to say. So design in this context, I see that as the service layer on top of the computing infrastructure, the jungle that is evolving underneath.
Yeah, really good answer. And I mean, as you're saying, I think the holistic view for it is really what you described. Like it can even be the programming language because someone has designed what it's going to look like. Yes, okay. I have loads of more questions, but I think I'm going to move to the questions that have come up in the chat. And just Gustav, just for your knowledge, we have one question about that some of us in the audience are students, and like what background do you need in order to get into this field in terms of previous studies?
Yeah, well, the good thing with design is that you can get into it from almost any background, so that I'd say both computing and design, or computer programming, AI, etc., are interdisciplinary fields that you can apply design to anything. You know, you can design objects, you can design services. So it really depends on what you want to do. a good way is to, well, I mean, of course, you can take the formal sort of programs and you can get into it. There's quite a lot to read about design online as well. As with coding, there's a lot of open source resources available. The good thing with design is that anyone can start designing. You can design on a very small scale at home. A lot of, just as coding, you know, you start at home, you start sort of playing around with things. I used to, I mean, before I moved into, I came to design school, I used to work with digital services a lot. So I used to, when I was playing around digitally, I was working with, you know, making little mock-ups and or setting up WordPress sites, testing things out on a small scale. And then gradually moving to a more professional and sort of more advanced, complex sort of products. But these days, since being at Design School, I also realized that there is a massive opportunity to combine physical making, IoT making, for example, with you can buy really cheap components online, and you can just start tinkering and fiddling with things, putting them together, connecting them to websites, to the web, to different things, and make what you want to make, essentially.
Let's see, Andrina, maybe you can go on mute. Thanks. Yeah, and Gustav, that also brings me to the idea of original thought, which I also know that you've spent some time in thinking about. And here in the AI crash course, we've previously mentioned OpenAI's most recent AI model called the GPT-3. A natural language model, and Gustav, how do you think this affects original thought, like captology in general, and what impact does it have?
Yeah, well, I think GPT-3 it's a really interesting example of a technology that has reached a fidelity level where it's so realistic that it's almost impossible to distinguish the texts that are generated by the AI from those written by a human, from the real thing. And as with any technology, it depends on how we use it and who uses it and for what end. You know, you can use nuclear fission to build atomic bombs, or you can use it to build nuclear plants. Well, I mean, some people don't like either, but you know. But it's the same thing with GPT-3. You can use it for good ends or for bad ends. But I think it opens up for a lot of interesting gray zones where in academia, all of academia is based on original thoughts. The idea that you're writing your own texts, you know, when you're applying for a university, you apply with a letter that you've written yourself. We started sort of nagging on authenticity when we started using spell checks. That's really the first tiny step, you know. It's 5% made by a machine. We do 5% of the text is corrected or, you know, improved by the machine. But what if that number goes up to 80% or 90%, or even if the texts are, I mean, even in GPT-3, you give it a bit of input and then it sort of puts something together. At what point, like, how much do we extend our agency using this particular technology? And more importantly, when do we use it sort of for deceptive purposes or for nefarious bad purposes? You know, where do we draw the line between what's acceptable to society and in different situations? So it just opens up for a lot of trouble that we need to fix, that we need to think through. Yeah,
and a lot of ethical questions, as you're mentioning. So it's a lot of discussions to be held around the area. And on that note, next week we're actually going to be focusing a little bit on ethical discussions. And how ethics is related to AI. But guys, I'm gonna open up to the audience or to all the participants. Does anyone have any questions that you want to ask?
Sophie.
Yeah.
We have a couple of
help me from the chat. Yeah.
Yes, we have a couple of questions in the chat. So one question is that what the UX UI designers do? Is it the same?
Yes, you could say that UX UI design is it's overlapping definitely with persuasive technologies, and I'd say it's even broader in a sense because it also incorporates social and cultural understanding and systems. So it's I would say it's a science of sort of persuasive systems rather than just studying the technologies. It's a bit broader in the context. But yes, it's definitely that. It's the interfaces, it's the user journeys, the service journey from that the customers go through in processes or users. So yeah, definitely.
Okay, and we have one other question. What do you think the role of the public sector can be to promote persuasive design to change people's behavior, such as wearing masks?
Yeah, that's a great question. There is already in the United Kingdom there is a government agency called I think the UK Behavioural Insights Team that are trying to figure out insights about the general population and then implementing policy through that. The same thing is going on in China. The government is gathering an awful lot of insights about the population and then implementing policy. So I think it's very contextual that governments will definitely start using this in different ways to implement their policies, whether it's mask wearing or if it's to prevent people from littering. A great question, I mean, moral question would be, for example, if you could design things that help people to quit smoking, should you do that? You know, should you run campaigns for anti-smoking, for example, even though it's paternalistic against some people's will, at least, you know, should you influence people without them being aware about it? So yes and no, I think is the fluffy answer. That we need to have processes in place to agree on these things. We need to have them fairly fast as well. And that's why, for example, forums like this or AI discussions taking place on all levels in government or in society are very useful because they help us to each form an opinion of what's right or wrong and then come up with collective rules for how we want to deal with it.
Yeah, great answer, thanks. One more question. Do you do any research into augmented reality and how it could be used to influence behavior, or is it too early to say?
Yeah, so I don't personally do any research into that, but I know there are researchers that have looked at augmented reality and also mixed reality and interactive mirrors, for example, where you you have a mirror. It adds an augmented layer of reality on top of the image, essentially, so that you to encourage you to exercise more or to exercise less or to see yourself as, you know, your ideal body type, and then you just look in the mirror to see how much exercise there is left to do. So people they are beginning to experiment with that kind of research. And the augmented reality, what else is there? I think that the more, as augmented reality also disseminates more and spreads more, that we start to use it more extensively, that it will also, then it will become a more potent tool for persuasion. But now it's sort of limited to those who uses augmented reality. The objects are still behind screens, like they're still not out in the physical world.
Yeah.
Very good answers, Gustav. Thank you so much. Ivana, did you have anything else on your mind?
There is one more question. Is most of the research and implementations of computer persuasion focus on marketing and increasing in consumption? What other areas of tech persuasion are being developed to improve environmental changes, for example?
That's a great question. Yes, unfortunately, most technologies that are persuasive technologies that are developed are used to either persuade people to buy stuff or to vote in certain ways. Because somehow influence, and it has always been, influence is power, right? So there is a very strong power dimension connected to the use of persuasive tech. So if you want, and getting people to buy stuff, that's very sought after power. Getting people to make decisions in certain ways in political processes as well. But there are many other uses. So for example, persuasive tech are used for getting people to exercise more. It's used in health care services to get people to take their medications on time, for example. It's used to, so these smart devices like smart watches or smart Fitbits or Apple watches are examples of smart persuasive technologies that we choose to use. And it's important also to mention that, I think, because not all persuasive technologies is imposed on us from other people. There's also technologies that we choose to use so that we change our own behavior or influence our own behavior. When we want support, you can also, I mean, if you want to be really hard, but you could consider a digital calendar, a persuasive technology in the sense that it guides and programs our daily behavior. But it's something we choose to use ourselves as well. Yeah, but those are a few examples I can think of. And of course, computer games generally, using persuasive tech for entertainment, for sort of getting people through processes. A lot of games, unfortunately, are connected to getting people to buy Smurf berries or coins, you know. So that's the issue, that, yeah, you choose to use this addictive, highly entertaining technology, but perhaps you don't want to buy Smurf berries for all of your salary, but that's what they are designed to support people in doing. So yeah.
I feel like when you're saying design, I feel like it can often be exchanged for the word like optimized, like it's about optimizing so many things. But this was just a thought I had now. Maybe, perhaps or perhaps not.
No, but you're right, and that's where cybernetics come in.
Okay, so that will be our second session.
Yeah, but I mean, the really one sentence pitch for cybernetics is that it's the study of goal-oriented systems. So as a GPS system, a system that is programmed with a goal, like a thermostat, for example. You set the temperature to 20, and it constantly sort of tries to keep the temperature in the room at 20 all the time. So that's a cybernetic system. And in design, persuasive systems are clearly cybernetic systems because they have a persuasive goal. It's a social goal. It's not a mechanical system. I mean, it is to some extent, but it's more a social cultural goal-oriented system. There's an awful lot to read about cybernetics and design and cybernetics and mechanical computer systems as well.
Yeah, could you maybe, Gustav, share some of that after this, just on that topic with me
absolutely.
or the group, and then I can share it.
I'm happy to do that, and I can also answer those questions that haven't been answered in the chat. So just hang in there, and I'm happy to keep chatting for a while.
Yeah, I'm super sorry to cut you off. I think we could spend several hours continue speaking about this, because it seems to be a great engagement, and I hope everyone found this as intriguing and interesting and important as I did. I really, really enjoyed this. Thank you so much, Gustav. And I'm gonna have to cut us off there, just in concern of time, because I know we're 18 minutes over time already. Well, but thank you so much.
Thank you so much. You've been a great audience, and that's amazing questions. I love talking about this, and thank you for giving the opportunity.
Yeah, we can tell, and I hope maybe an idea is to have a catch-up, or follow-up session on this when we speak about cybernetics, to be continued. Yeah. And I'll hand back to Peter just on the very last seconds. Keeping time is not our strength, I think. But that's because we have so much fun.
it's both really interesting and everyone is so engaged. So we don't want to cut people off. And Gustav, thank you so much for a super interesting talk. You made me want to apply to the masters in UX design instead of do working in this spring. So thank you for that. Great, guys. Thank you so much for attending today, both to Gustav and Sheetal, and to you, all of the participants, for the fantastic energy and the engagement you put into this. We are so thrilled. We just want to go through real quickly. So we will do the future with AI within 2 weeks. So Wednesday, 2 weeks from now, it will be entirely digital as well. And for those that don't have the link to the AI Crash Course Drive, you can use the QR code here through your cell phone. I'll give you just a couple of seconds to do that. Then you can access a lot of the documents, our learning playlists. We also will put in some of the links we've discussed today about the BJ Fogg, for example, the Tiny Habits book and his TED Talks. I also put in a link to Gustav's TED Talk, I think, there, and we will put a link to the playlist we have with all of these sessions. So guys, thank you so much. If you have any questions, reach out to either Sophie or myself. And if you have suggestions for topics that you want to discuss, if you have suggestions on speakers you would like us to talk about, just reach out. And we will send you an email tomorrow morning with all of the links we discussed here today, and also the YouTube video of today's session. So have a great evening, take care, and stay away from people that you don't know and that you don't live with. And I hope to see you here again in 2 weeks.
Thank you.
Thank you very much. Bye.
Thank you. Bye.
Thank you. Bye-bye.
Bye-bye. Thank you.